Hi, this is Charlie Thompson, and welcome to Introduction to Physical Geography. This is the first lecture, and for all the chapters that we'll be going over this semester, I'll put up a video of the lecture slides with me talking over them to explain things, give you some context, background, details, fill in the blanks, so that they're not just lecture slides presented in a vacuum. So this first chapter is Intro to Physical Geography. And here's the big topics, the way the book is organized, and I'll also include things that are important about learning. Just general, broader, beyond just the chapter stuff. For example, the way the book's organized, it's obviously organized into chapters, but then each chapter is divided up into 2 or 4-page modules. So the first module is the world around us, the second is the science of geography, and so on. And each chapter is organized around big questions, broad questions. Not really specific detailed questions, but broad questions like, what is physical geography? How are locations on Earth located, mapped, and divided into time zones? What tools do geographers use? So those are some of the big questions that we'll be asking and hopefully answering in this chapter. And one of the things I like to start with is about what geography is, what geographers do. I know when I started geography, I had virtually no idea what geography was about. I didn't take it in high school because it looked boring. When I got to college, I realized that I already loved geography. I just didn't know that that's what geography was. So this is a map from the 2000 presidential election, and the blue areas went Democratic and the red areas went Republican. And some geographer looked at that and said, oh, that's interesting. There's this big stretch, and let me turn on the pointer. There's this big stretch right in here that is unusual because it's a lot of people voting democratically in a sea of red. So what's going on with that? And they said, if you look at the patterns of cotton production in 1860, there's a really good agreement between the patterns of Democratic voters and cotton production. So this would have been cotton. It would have been picked by slaves. And so what we're seeing, although it's actually a map of cotton production, what it's telling us is where African Americans would have been living as slaves in 1860, where they would have been producing cotton. So massive amounts of cotton in here, Louisiana and Louisiana and Mississippi, but then through Alabama and Georgia, that's a little less clear. This makes a lot of sense to me. It's by the Mississippi River, so you've got access to the river. Because the river floods, you'd have good soil, but this was well inland and away from big rivers. And in fact, one of the things geographers got into a couple of years ago is mashups, where you take 2 different things and slap them together. In this case, we've got the dots showing cotton production and the blue-red spectrum showing voting patterns in 2000 again. So now you can see that there's really good agreement between cotton production, and I always wonder what happened here. So there's lots of cotton production, but it's all Republican. Did African Americans move out during the 1960s with the movement of African Americans out of the prejudiced and bigoted South to elsewhere for economic reasons, for cultural reasons? So now we've got a better idea, and at least at this point we know to understand the 2000 presidential election and to understand the 2020 presidential election, you have to go back to 1860, but that doesn't answer the question, why were they growing cotton there? And to answer that question, you need to look at soil. This is a map of soil. So here we have Mississippi and Alabama, and this is a specific one particular type of soil called the black soils, and it's really good for growing cotton. But why that shape for growing cotton? And to answer that question, we need to look at the way North America looked about 85 million years ago. So 85 million years ago, that was a shallow sea. So this would have been an area that was all underwater 85 million years ago. So the rocks that were deposited 85 million years ago eventually became soil that was good at producing cotton, that led to high proportions of African Americans in that region. That persists to this day, that explains the pattern of voting. So that's one of the things that geographers do, is look at something and try to look at something spatial That's one of the keys to geography. Geographers do spatial analysis. Spatial analysis is just trying to figure out where things are, where they're not. Why are they there? Why are they not there? Did they used to be there? Have they never been there? Spatial analysis is just looking at where things are. Volcanoes, earthquakes. There's patterns to all those things. So as geographers, we try to understand what's behind that pattern. Again, here's a blowout 85 million years ago. There was no Hudson Bay. That's a relatively recent phenomenon. Hudson Bay exists because of the massive ice sheets that were over Canada about 20,000 years ago. The sheets were so thick that they've actually pushed the crust below sea level. And now that the ice has melted, Hudson Bay is bouncing back up. But here we have a massive interior seaway. This would have been a shallow ocean. You can see California doesn't really exist yet. We've got the beginnings of some of the rocks that would become the Coast Range and some of the rocks that would subduct to become the Sierra Nevada. The Atlantic at 85 million years ago was smaller. It was still opening up. So to understand voting patterns today, you really got to go back a while. So what else do geographers do? Just looking at the world around us, we look at systems. Systems are sets of stuff linked by flows of energy. And then let's look at some of the, and as I'm looking at this, I just realized I want to redo it all because these events, while they're important, they're not really current, but they're good. So let's talk about them. They're in the book. We've got the Elwha in Washington, Jalisco in Mexico, the Atacama in Chile, Kathmandu in Nepal. We've got Kampong Speu province in Cambodia. So the Atacama is one of the driest places in the world, but a couple of years ago they had massive wildflower blooms. That was unusual. And flooding. In fact, the flooding was so severe it killed people. So it's ironic to have people dying in a flood in the driest desert in the world. The 2015 earthquake in Nepal, there's only a couple places on the planet that get really massive earthquakes like this. Alaska's one, Chile is one, Indonesia, Nepal. To a lesser extent, the San Andreas Fault. It's a different type of mechanism. We'll talk about that later. But again, the idea that there's patterns, there's only certain places that get big earthquakes is part of physical geography. Dam removal. In the 1950s in the United States, we put up all these dams across the West to try to exert control over the landscape. And then it turned out a lot of those dams were counterproductive. They were actually hurting the environment more than helping the environment. And so they were taken out, destroyed, removed, so that salmon runs would be able to be reestablished. So we'd have a healthy fish population. Hurricane Patricia at the time was the strongest hurricane ever recorded, sustained winds of 200 miles an hour in the Pacific, the strongest Pacific hurricane. Cambodia, using GPS units. This is a GPS receiver. It is an older commercial unit. Everybody's phone these days has a GPS chip in it that talks to satellites to establish your location within a couple feet. And in this case, they're using GPSs as part of a land reform effort. Other uses of GPS include clearing landmines for farmers so that farmers can farm once again instead of not being able to farm, or farming and worrying that they'll be blown up when they discover a landmine. So next up, the science of geography. What is geography? So the literal words geography mean to write about the earth. One of the most important part about geography, I would say for today, is spatial analysis. Geography is all about spatial analysis, where things are, where they aren't. As a geographer, the scope of geography is massive. You can study anything you want as a geographer. Geography is often divided. The big split in geography is dividing up geography into human geography and physical geography. And with human geography, it's close to history or economics or anthropology or sociology or political science. The difference would be, again, spatial analysis, that geographers would be studying factors, ideas, concepts that anthropologists or economists or historians would be studying, but they would also be trying to find that spatial aspect to it. Physical geography, the other half of geography. Biogeography is the study of plants and animals and where they are. Geomorphology is the science of landforms. Soils, geographers study soils and climate and weather. At this point in my career, I just consider it geography because there's no physical place that hasn't been affected by people, and you can't find people that aren't affected in some way or influenced by their environment. So I think there's considerable overlap. On the other hand, you can't just have the one big class that would just be called geography. So to split it up, we've got biogeography and historical geography and economic geography and cultural geography and climatology and meteorology and all the specialized aspects of geography. Here's another view of the same thing, dividing up into physical geography and then human geography. An outstanding example of medical geography, and now I would have to say the most interesting medical geography or the most relevant and important would be looking at COVID and the medical geography of COVID. But an early example, a very important example, was 1854 in London. In London in 1854, they didn't have running water. So these would have been apartment buildings in this neighborhood. People would have been living in apartment buildings. They wouldn't have running water. There was no running water coming into the house, no running water coming out of the house. So if you wanted water, you had to go to one of these X's, and the X's all represent water pumps, public water pumps that you'd go to get your water. So you'd go fill up your water, you'd bring it home, and your extra water, for example, you wake up in the morning, you go to the bathroom into a pot, and then what do you do with it? The answer, it turns out, in London was you dump it in the basement. The basements had dirt floors, the liquid soaked into the floor and went away, out of sight, out of mind. I don't see it, I'm not going to worry about it, except that in a cholera outbreak, cholera is a waterborne illness. So these people were getting water from, as it turns out, a pump that was contaminated. And unfortunately, the Broad Street pump, you can see the X right here, and the cluster of dots. The Broad Street pump had a reputation for having better tasting water. So if you were between two pumps and you lived midway between that pump and the Broad Street pump, you'd go to the Broad Street pump because it had better tasting water. Unfortunately, the water was contaminated. People would get sick. They'd go to the bathroom. They'd dump it in their basement. The basement shared by everybody, and then that would then contaminate the drinking water. So they made this map. John Snow made this map. It's a dot map, so each of these dots represents a dead person. And looking at the map, it's a great example, not just of early medical geography, but it's a great example of the power of geography. And that is, you look at it and you know where the dots are. And it's very easy to look at the dots and say, oh, yeah, if you're going to close a pump, close that one. So they took the handle off the pump, they shut it down, and this cholera outbreak went away. And as a result, it's probably the most famous example of medical geography that you'll find. Dr. John Snow in 1854. So a big part of geography is it's science, and we use the scientific method. And the scientific method is a tool to find out what's real, or rather what's true. The scientific method is a tool to find out what's true and what isn't true. So in order to use the scientific method on something, you have to be able to prove that it's true, or you have to be able to prove that it's false. If it's in between, you don't get to use the scientific method. It just doesn't work. To use the scientific method, you have to either be able to prove it, it has to be provable, or disprovable. So things like the existence of God, utterly outside the scope of the scientific method. Things like, is the climate changing? That's totally legit. So let's see how the scientific method works. As I said, it's a tool for finding out what's true and what's false. It's based on evidence. It's based on experimentation. It is supported by facts. It is really unfortunate that the end result of the scientific method is a scientific theory, because when we use the word theory, we use it and it means two different things. Scientists mean it is a well-tested, well-researched, tried and tested result of the scientific method. It is better than facts. It is supported by multiple facts. That's one way we use the word theory. The other way, it's just an idea. So unfortunately, the end result of the scientific method is a scientific theory, which scientists understand, but often non-scientists don't understand. So people get confused and say things like, well, you can't teach evolution. It's just a theory. To which the scientists say, yes, it's a theory. That's why we're teaching it. So the way it works is you need to start with, well, you want to find out something, observations. Let's start with global warming. Is it getting warmer? Yes. This last decade was the warmest 10 years ever recorded, which beat the last 10 years before that, which beat the last 10 years before that. Yes, there's absolutely no doubt that the planet is warming. So questions, variables, is it warming every place? Yeah, pretty much. Hypothesis. Well, this is where you get to make guesses. I have an idea. I think the climate might be getting warmer because we're getting closer to the sun. So you test. Are we closer to the sun? No. Okay, that didn't work. We go back to the drawing board, try to come up with another hypothesis. Because really, if you think about it, if the planet's getting warmer, there's only two reasons it can be getting warmer. Either more energy is coming into Earth, which is causing it to warm, or if the same amount of energy is coming into Earth, something is trapping the heat and keeping it from leaving. So we can look at all the reasons that more energy would be coming in. Is there more energy from the sun? We can test that. The answer is no. So it's back to the drawing board. Are we getting closer to the sun? No. Are we getting more energy from the sun? No. Okay. So then, after scientists have looked at all the possible reasons we could be getting more energy, the answer or the question then has to be, is there something that's keeping the heat from going back out from Earth to space? And the answer is yes. It's greenhouse gases. We've known this since the 1800s. It has been tested and tested and tested. The atmosphere acts like a blanket. We've known since the 1800s that carbon dioxide absorbs heat. And as the amount of carbon dioxide increases in the atmosphere, the temperature of our planet increases. So in order to come up with a different hypothesis or a different theory, aside from it's humans creating greenhouse gases that are absorbing heat and trapping the heat so that it's not going out into space as fast, you'd have to explain why CO2 isn't trapping gas, why it isn't trapping heat anymore, why the gas isn't trapping heat, and you'd have to come up with another mechanism, explain where the warming is coming from. And so far, scientists have been unable to do either of those. So we're stuck, unfortunately, with now the well-established theory that the reason that the planet is getting warmer, hypothesis, the idea, because of carbon dioxide and other greenhouse gases. Did we test this? Yes. Did the results match our hypothesis? Yes. Boom, you got a theory. So global temperatures, up and up and up. This is just going back to 1880. So this is the instrumental record of actually looking at thermometers back to 1880. Here we have in yellow energy from the sun and temperature. You can see the temperatures continue to go up, even though the energy from the sun was going up for a while, and it's kind of fizzling now. And yet the temperatures are going up and up and up and up and up. In fact, there you can see the hottest year ever recorded. So it also turns out the amount of carbon dioxide is the highest it's been in at least 1 million years. So when carbon dioxide levels were higher, we had an interglacial period, and then we had about 90,000 years of cold. So you've got 3,000 feet of ice over Chicago. Warm like the present, 3,000 feet of ice. Warm like the present, 3,000 feet of ice. Warm like the present, 3,000 feet of ice. Warm like the present, 1,000 feet of ice. Warm like the present, 3,000 feet of ice. CO2 has gone up between about 180 and 280 parts per million, and CO2 now is up over 400 parts per million. There have never been humans alive on Earth at a time when the CO2 was this high. The last time CO2 levels were this high, humans had not evolved yet. And then all of the reasons that scientists have looked at. Air pollution makes us a little cooler. Clouds make us a little cooler. But greenhouse gases make us warmer and warmer and warmer. And some kinds of pollution actually make us warmer as well. This is black carbon from diesel exhaust or ocean-going shipping. Creates black soot that then absorbs heat. So the net effect is we're warming the planet because we're humans. And we burn fossil fuels. A really, really important idea, super duper important, is population growth. That up until about 1800, the world had fewer than 1 billion people. So we hit 1 billion around 1800. Around 1920, we hit 2 billion. In 1959, we hit 3 billion. 1996, we hit 6 billion, 7 billion. We're on our way to 8 or 9 billion. But you can see the growth years before present. So here you've got 0, 2000. Most of the population growth. In fact, from the time that I was born until the present, we have more than doubled the population of Earth. So much of this population growth has been very, very, very recent. And it's kind of interesting. This rapid population growth has caught humans unaware, unprepared, much in the same manner that the equally rapid COVID growth caught humans unaware. Exactly the same as CO2 growth has caught us unaware. All of these things, population and CO2 and COVID, if we had dealt with it earlier, tried to find a way to fairly and equitably reduce human population, it would have been much easier. If we had started phasing out greenhouse gas producing, if we had stopped using fossil fuels, it would be way easier to deal with global warming today. If we had had masks, mandatory masks and shelter in place across the U.S., we could have stopped COVID. Here's a video. I'm not going to play it now. I really recommend I'll put a link to it in the lecture notes so that you can watch it on your own. It is the last 2,000 years of human population growth, and let's get it started. Here we start around 1800. There you go. We've hit 1 billion. 1900. Going to hit 2 billion around 1920. There you got 2 billion. And then it just takes off like a rocket ship. 3 billion, 4 billion, 5 billion, 6 billion, 7, 8, 9. We don't know. Most of the people live in Asia. If you wanted to go, if you really like people, if you're a people person, you should move to either South Asia or East Asia. If you really don't like people, you should go to where the deserts are. Desert, 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 or the places that are frozen. Frozen, frozen, frozen. Another view of the human population map. East Coast is very dense. Much of the West, not a whole lot of people there. The Amazon still, not a whole lot of people there. Very few people in the Sahara. Very, very few people in the rest of Australia. Tibetan Plateau, the deserts in Central Asia, and then the frozen parts of Russia. Low population density. This is the world at night. So in this case, the electric lights are a proxy, not just for population, but also development. You can see Africa, over 1 billion people in Africa, which is 3 times the population of the U.S. So there's 3 times as many people in Africa as there are in the United States, but you can see there's just a handful of places that have a lot of lights. It looks like Nigeria and then Zimbabwe. Either Botswana, South Africa, Zimbabwe, that region in there in Africa, very high population density. I love the Nile. Oh, this is South Korea. This is North Korea. That's Pyongyang. They keep the lights on there to impress the tourists. But the development gap between China, North Korea, and South Korea is pretty amazing. This is taken from the International Space Station. So humans, incredibly important in geography. Humans related to the idea of sustainability, which is a buzzword. It's a popular idea. People love the idea of sustainability, but there's no alternative. I mean, if sustainability is the ability to do whatever you're doing over the long term in a way that minimizes impacts on the environment so that you can keep doing that thing, there's nothing about American agriculture that is sustainable. It will be impossible to continue doing agriculture the way we do in the United States in the long run. So we're going to have to change. Organic agriculture, this small-scale agriculture like this clearly won't feed the entire U.S. the way everything is set up now, but it might be a good way forward. Small farms are economically more profitable. Small farms use less energy, they use less resources, and they make more money than large farms. But large farms are owned by corporations who have more money than humans, than individual people, and so they can get laws written that then favor large corporations, large corporate farms instead of small-scale farmers. Despite the fact that the small-scale farmers can grow more food using less input, using fewer inputs, making more money than large farms. Related to this is the ecological footprint. Ecological footprint is the idea that you can quantify the spatial requirements for your lifestyle. In fact, I think I just figured out this is going to be your first Wednesday discussion. I'll put up the link to the ecological footprint website. You can calculate how many Earths would be required to support if everybody on the planet wanted to live like you. You can go through the ecological footprint calculator, footprintcalculator.org, and calculate out how many Earths would be required to support somebody. If everybody in the world wanted to live like you, how many Earths would be required to support those resources? That's a pretty good place to stop. I'm going to pause this video for now. Last semester, I recorded longer ones. I think putting them in blocks of, 1, 2, 3 modules rather than trying to get through the whole chapter will work better for everybody. So I'm going to call it quits for modules 1 and 2 of the first chapter. I'll post those to YouTube. I'll put up the link on Canvas, and I'll get to work on the second video for the first chapter. That's it. If you have any questions on anything, if you have any suggestions, hey, it would help me with your videos if you could do this. I really, really, really would appreciate that. I'm making these videos for you, doing the best I can. I'm sure I can do much better. Please let me know what I can do to help you be a better student. That's it. I hope you enjoy the first chapter.